Alright, gang. This is the start of Unit 4. And as far as like an entire semester goes, we're finally putting trigonometry behind us. The first 3 whole units were basically all on trigonometry, but there's other kinds of functions to learn about. So, I mean, if you really stepped back and looked at like the big picture, ever since your beginnings of algebra, you've been learning about all the different kinds of functions, you know, as you work your way towards, you know, like calculus, perhaps. So you probably started off with like linear functions, and there was other kinds of functions. Quadratics, you probably spent a lot of time on quadratic functions. You know, a little bit of absolute value functions, square root functions, cubic functions. There's a handful of them there. And then this semester, we learned about the trig functions. You know, y equals the sine of x, y equals the cosine of x, y equals the tangent of x, and so on and so forth. And there's just like a couple more to learn about as far as like completing your education on functions. And so 4.1 is about exponential functions. And exponential function makes me think of exponential growth. All right, so as opposed to, say, linear growth. Linear growth is you're always making the same the same increases. Kind of like, you know, let's say you were getting paid an hourly rate at, say, McDonald's. Let's say McDonald's was paying you $8 an hour. You know, in the first hour you'd make $8. In the second hour you'd make $8. Third hour you'd make another $8. Fourth hour you'd make another $8. And every hour you make like another $8. That jump of $8 is consistent. You know, it's like that constant rate of increase. You know what I mean? And that's a linear model. That's linear growth. You know, where that slope, you know, like the slope of a line, that slope is always the same. Okay, you know, up $8 over 1 hour, up another $8 over an hour. That's linear growth. Exponential growth would be when the jumps are actually getting bigger. You know, like how much money is being increased. Like those jumps are getting bigger. So, for example, exponential growth. These are not precise numbers or anything, but let's say in the first hour, McDonald's paid you $8, but then in the second hour you got paid $10, and then in the third hour you made $15. You know, so your hourly amounts are getting bigger. And then in the fourth hour you made $22, and then in the fifth hour you made $30, and just like the increases are growing. Okay, that's exponential growth. And starting off with an example here, talking about like the Space Shuttle Challenger, the shuttle that tragically exploded back in 1986. And the tragedy involved damage to O-rings in the engine. And basically, the number of O-rings damaged increases dramatically as temperature, and this should say falls, not fails. So a little bit of a typo there. So basically, as the temperature got colder, as the temperature fell, you know, the number of O-rings that were probably going to become faulty was going up. And here is a function, an equation that represents a function. So this equation represents that relationship where x is the degrees. So the temperature is x, and all this would equal f of x, which is like the number of O-rings expected to fail. And quick question, do you notice anything about this equation, this function, that's different from any other functions you've seen before? Perhaps you notice that, man, I don't think I've ever had the variable be the power. You know, yeah, like we're raising something to the x power, and that's what pretty much, it's the big, it's the big, indicator that what you're dealing with is an exponential function. But here's like more the official textbook, like what what really defines an exponential function. And so it's going to be f of x or y, whatever, they're interchangeable. F of x equals b to the x power, you know, some base b to some power x. And here we have some fine print, as you'll often see like in textbooks and mathematical definitions. So we have some like specifications, some technicalities. You know, they're basically the fine print here is that this base b has to be greater than 0, and it's also not allowed to equal 1. And if you're asking like why don't they just say it's got to be greater than 1, well, don't forget about decimals and fractions. You know, your base is allowed to be like 0.5 or 0.6 or 0.01, whatever. So this base has to follow these rules. And the exponent, you know, and it's going to involve a variable of x or whatever, and it's just got to be like real. So x works, but also x plus 3, 2x minus 7. I mean, anything that could be real, you know what I mean? And so looking down here, just quick little activity kind of thing. Circle all the functions that qualify as exponential. And little f qualifies. It's got a good base and variable in the power. Not little g, because the base is not allowed to be 1. And I guess really quick, it doesn't take a whole lot of time to figure out why the base can't be 1 or why the base can't be 0. It's like, imagine if the base was 0 or the base was 1. If you had like 0 to a power, that would just always be 0. And if you had 1 to a power, that would just always be 1. So little g, no good. Little h, no good, because who's to say that this base of x couldn't be negative or 0 or whatever? So little h doesn't work. Like, your base can't be a variable. Little j works. It's got a good legal, that's, you know, base that's allowed of 2, and x plus 1 is good for your power. Big F, nope. Same reason of little h. Big F is a no. This is actually cubic. Big G is a yes. Big H is a no because of the illegal base. But big J is good. So those are what exponential functions look like. And then really quick, as far as evaluating exponential functions, it's the same thing as evaluating all the other kinds of functions you've worked with in the past. You know, evaluating a linear function, evaluating a quadratic function. All we're going to do is, well, let's see if you can figure it out on your own as we look at this. On the morning Challenger was launched, the temperature was 31 degrees Fahrenheit. Find the number of O-rings expected to fail in that temperature. So what do you think we're going to do to evaluate? Well, wasn't x the temperature? and they're giving us a temperature. So all we're really going to do is plug in 31 for x. And that's going to basically get us going with evaluating this function, just kind of like plugging something in for the x variable. And then if you have a calculator handy, which I hope you do, you should, see if you can push the correct buttons and punch all this in. 13.49 times 0.967 to the 31st power minus 1. Okay? Punch those into your calculator. It should be able to handle all of this at once. All right? And it should be able to do the order of operations in the correct order, which would be, first you would raise this number to the 31st power. Then after that you would multiply to the 13.49. And then you would subtract 1 in that order. And the calculator knows that, and it's programmed to do that correctly. But remember about PEMDAS. Please excuse me, dear Aunt Sally. Exponents come before multiplying, okay? And if you've punched it in correctly or done the steps in the correct order, you should get about 3.767, which, you know, so that, what does that mean? That means like 3 or 4 O-rings could fail or be expected to fail, you know, when the temperature is 31 degrees. So that's evaluating. Again, it's nothing new, plugging numbers in and just crunching the math. Let's move on to graphing. And this is also kind of familiar because we're going to look at, like, figure out this graph the same way you probably figured out other brand new equations that you never graphed before or never saw before. We're going to make a table just like this. And it looks like we're going to use the, you know, very, very common numbers to plug in for x, and we're going to get a number that's essentially y. Remember, f of x is just like y. And those will be just a bunch of points. It looks like we're making 7 ordered pairs, and those are going to be points on this graph to be. All right? So you might want to pause the video, you know, and see if you can plug in -1 in for the function, see what you get, and then plug in -2 in for the x and see what you get, and then unpause. I'm going to remove these in 3, 2, 1. But plugging in all of these x values separately, you should get these values for essentially y, right? So this would actually be -1, 0.5. And this one would be 0, 1, for example. And this would be 3, 8, you know. All of them are like that. And I want to remind you right now that, hey, when you raise something like 2 to a negative power, that doesn't mean you're going to get a negative answer. That's not what negative powers are. So 2 to the -1 power just makes it into like 1 over 2. And 2 to the -2 power just makes it into like 1 over 2 squared. So remember that about negative powers. And so now we want to graph all these points. So let's start with this one, I guess. Why not? 0, 1 is right there. 1, 2 is right in there. And then 2, 4, I'll graph that next. And then 3, 8 would be about right there. And then -1, 1/2 would be like there-ish. And then -2, 0.25, about right there. And then -3, 0.125, or 1/8 would be like kind of right there. So look at those dots. Looks like they're forming some kind of curve. And I want to ask you at this time to think about, well, what if I plugged in other x values? I mean, well, really quick, if I plugged in like 1.5 in for x, I'm probably going to get somewhere around 3, probably not exactly 3, but, you know, it looks like I would have a dot like right there, you know? But what if you plugged in 4, you know? Look, what if I plugged in 4? What if I plugged in 5? What if I plugged in 50? What if I plugged in 500? You know, what kind of point, where's this graph going as you plug in further and further x values to the right? Like, what's 2 to the 50th power? You know, this graph is just skyrocketing up so fast. I mean, just plugging in 4, you'd be all the way up at 16. Just plugging in 5, you know, as an x-coordinate, you'd be all the way up to 32. Right? So this is just blowing up, right? But, I mean, look, it's just kind of shooting up super fast. But what if you kept this graph going to the left? What if you plugged in -4? What if you plugged in -5? Think about it. What if you plugged in -50? What's 2 to the -50th power? What if you plugged in -1,000? You know, which is like way off this way, but oops, sorry about that. I mean, what is 2 to the -1,000th power? I mean, what kind of answers are you getting for y? What kind of points? Where are those points going to be? Are those points ever going to be actually negative? And the answer is no. They're going to get really, 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 really small, really fast. But isn't it always going to be above 0? Aren't we going to get like closer and closer and closer and closer to 0, basically closer and closer to the x-axis, but never, ever, ever touch it? Which means actually what we have here, remember with the tangent graph, we had a vertical asymptote? Well, what we have here is actually like a horizontal asymptote, kind of like that force field wall that your graph can like never quite get to, even though it gets closer and closer and closer and closer and closer to it. So you want to get in the habit of including that on your graph, like this dashed line representing your asymptote. And so that's what an exponential function graph looks like. This curve that just creeps closer and closer to a horizontal force field, but just keeps on going to the right forever, but goes up really fast as it goes to the right. And this is exponential growth, man. You know, like here, we increased by 1 and only increased by 1. But then when we increased again, we went up by 2. But then when we increased again, we made a jump of 4. The next jump is going to be a jump of 8. And then it's going to be a jump of 16. The jumps keep getting bigger and bigger and bigger and bigger. That's exponential growth. And that's why the graph looks like that. Fast tracking this second example of a graph, this is 1/2 to the x power. And if you want to pause the video, you have like 3 seconds to do it. Pause the video. Here's what the table, and so you can do it on your own. But here's what the table's going to look like when you plug in these values for x into this equation. And so when you plot these points like, you know, -2, 4, or 2, 0.25. I just want those to be purple. So plotting all these points like -1, 2, which would be right there, I do believe. -2, 4 would be like there. -3, 8 would be like there-ish. 0, comma 1 again. Remember, anything to the 0 power, you're going to get 1. Anything to the 0 power, you're going to get 1. And then 1 comma like 1/2, about right there. And then here like 0.25, and then here. Look, this is it's like this is happening just in the other direction. You know, as you plug in, you know, smaller and smaller x values in the negative direction, you know, like -5, -10, -12, -50. That's when you're just blowing up super fast. But as you plug in larger values like 4, 5, 6, 7, 8, 80, 800, 8 million, you're just getting closer and closer to 0, but never actually hitting it. So make sure to include this horizontal asymptote. And that's what that graph looks like. It's also exponential, of course. And, spoiler alert. Darn it. Oh well. I guess there was a good chance you were going to do this on your own anyway, for realsies. But this last little activity, I guess won't really be much of an activity, huh? After all. So kind of changing gears a little bit, even though this is definitely still in the world of exponential growth, okay? Like absolutely, this is still related to exponential growth, but it almost seems kind of like its own thing in these notes. The natural base e, okay? Now, really quick, if you take this, 1 plus 1 over n, all to the n power, and you just keep plugging in larger and larger values for n, right? If you just plug in 1, this is the answer you get, plugging 1 in for n. If you plug in 5, this is approximately what you get. If you plug in 10, you get this answer. 100, bam. Plug in 1,000, this is what you get. Plug in 100,000, this is what you get. Plug in 1,000,000, I mean, you're not going to get exactly the same thing, but if you're only going to 3 places, you still just have 2.718. And again, if you plug in 1 billion, again, it's going to be different technically, but as far as just like 3 decimal places, you get like 2.718. Here's what's happening, okay? There is this weird irrational number, kind of like pi. Okay? You know how pi is some crazy irrational number where the decimal goes on forever and ever and ever and ever and ever and ever and ever? This is another one of those situations. So you can pretty much think of this number e. So again, we're using a variable. Pi is kind of like a variable or a symbol that represents just a number. It's a weird number that just happens to pop up here and there when we're working with like circles and stuff. But guess what? This number, it's called like Euler's number or the natural base. This number also pops up in nature, in exponential growth, all over the place. So you can start to think of like this number for e pretty much being like 3.14 is pi, you know, because, and the precise technical definition of what this number is, it's what this approaches as you let n just get infinitely bigger, like forever. So you could plug in like 1 trillion. You could plug in 900 trillion, and you're just constantly zeroing in on what this number actually is. But you can just pretty much think of it as about 2.718. You know, kind of like we think of pi as just 3.14. Okay? So don't be surprised if you see e, which is just now a number, just pop up all the time in future weeks, okay, for us. Or even future years, okay, like going into calculus class. You got to become familiar with this. And just like pi you can find on your calculator, you can find e on your calculator. Probably like this, but this will probably be like a button on your calculator. But if you type in just e to the first, it's, this number is going to pop up, which is e. E to the first is e, right? E to the first is just e. And so that's pretty much all there is to kind of cover in section 4.1.